Coulomb's force law can be the basis for estimating the net charge on an object. Conservation of charge and Gauss's law are also the basis for the measurement of charge. Coulomb's force law states that a particle or object carrying a net charge Q2 in an electric field due to a second charge Q1 experiences a force proportional to the product of the charges and inversely proportional to the square of the distance r between. Charges of the same polarity repel. In this demonstration, the particles are air-filled balloons of the variety used at parties. They can be charged by rubbing them with a dry cloth. They repel each other because they've been charged to the same polarity. Let's use measurements of the separation distance and the weight of the balloon to approximate the charge that's been left on one of the balloons. The threads that have been used to suspend them are tied at a common point. We can measure the vertical distance L between the height of the balloons and the point where the threads are tied. We can also measure the distance r between the balloons. The balloons are not all that small compared to these distances. However, for the purpose of estimating the charge, we'll represent them as point charges and point masses. There are three forces acting on the right balloon. The downward vertical force of gravity, the balloon mass times the acceleration of gravity g, the horizontal Coulomb force of repulsion, and the tension supplied by the thread. To have the tension of the thread balance the gravitational and electric forces, the ratio of the Coulomb force to the gravitational force must be equal to the ratio of half the distance between the balloons, r/2, to the vertical distance from the balloon to where the thread is tied. If we assume that the balloons are equally charged, we can express the Coulomb force in terms of the spacing between balloons, r, and the desired charge q. This expression can be solved for q as a function of the quantities that we can measure. Having measured the balloon mass m, the spacing r, and the height l, we can deduce q. First, we weigh a typical balloon. The mass m of this balloon is 0.73 grams. In MKS units. The gravitational acceleration is 9.8 meters per second squared. The spacing between balloon centers is about 50 centimeters. It's not possible to put the meter stick close to the balloons without their being attracted to Professor Zahn. His body's a good conductor. The charges on the balloons induce image charges of opposite polarity on conducting surfaces, to which they're attracted. The height L is roughly 1 meter. Finally, the permittivity of free space is 8.85 times 10 to the minus 12 farads per meter. Evaluation gives a charge Q of about 220 nanocoulombs. Conservation of charge and Gauss's law can also be used to deduce the charge on the balloons. This will be done by putting the balloon inside a conducting enclosure and measuring the charge induced on the enclosure. Note that this induced charge is opposite in sign to that of the balloon. This image charge is just that responsible for attracting the balloons to any essentially grounded conductor in its vicinity. By making this metal enclosure, which is called a Faraday charge, the Faraday cage is insulated from a surrounding grounded shield and itself connected to ground through the low impedance of an integrator. The shield is necessary to prevent field lines from outside charges terminating on the cage, such as from Professor Zahn's having walked on the carpet. Because the enclosure is its little electric field between it and its shield, the integral form of charge conservation shows how the charge induced on the Faraday cage is related to the current I to the integrator. The surface S encloses the cage completely and cuts through the wire. The only contribution to the integral of the current density is where the wire passes through the surface and is the current I. Because the charge on the outside of the Faraday cage is 0, the net charge in the volume V enclosed by this surface is the negative of that brought inside the cage as the balloon is in rate of change of the charge introduced into the enclosure with the balloon. If the balloon is finally complete, then the final value of this charge is just that on the balloon. This is true even if the balloon makes no electrical contact with the Faraday cage. The integrator is made from an operational amplifier, and the integrated signal could be displayed on an oscilloscope. Instead, we'll use an integrating electrometer in Coulomb measurement mode. It's designed to display the charge that would account for the integral of the current into its input. The shapes of the Faraday cage and grounded shield do not matter. In our experiment, the Faraday cage is a waste paper basket-sized rectangular aluminum box, and the surrounding shield is a metal screen. By now, one of our balloons is broken. But with new balloons and a renewed charge, the spacing looks to be about what we had before. Here's what happens when we insert the balloon in the Faraday cage. Watch the meter, too. Our charge conservation statement can be used to see that it makes no difference to the measurement whether the balloon makes physical and electrical contact with the inner box. From the dial settings on the top scale, a full-scale deflection is a charge of minus 1,000 nanocoulombs. The measured charge is 220 or 30 nanocoulombs. Let's see what we get for the other balloon. The reading's about the same, about 220 nanocoulombs. Remember, from our force experiment, we estimated 220 nanocoulombs. Of course, given the informality of our experiments, this agreement is somewhat fortuitous. Both the electromechanical and Faraday cage measurements that we have illustrated can be made very precise. Here, we've illustrated how Coulomb's force law, the law of charge conservation, and Gauss's law can also be used to make rough estimates. When the balloon is removed, the meter reading almost goes back to zero. Apparently, the charge is essentially removed with the balloon. What happens to the charge on the balloon if it's broken while in the Faraday cage and then removed? We've used Scotch tape to hold the balloon together. Professor M.Zahn feels that most of the balloon was removed. The charge was not.
A classic application of Ampere's integral law is to the prediction of the magnetic field of a line current. Ampere's integral law states that the integral of the magnetic field intensity around a closed contour C is equal to the net current, conduction plus displacement, that passes through the surface S that is enclosed. The integral of the magnetic field intensity around a closed contour C is equal to the net current that passes through the surface S that is enclosed. In this demonstration, the current density and associated fields are at 60 Hertz. Current essentially extends to minus and plus infinity. This line current passes through a surface S enclosed by this contour C. Ampere's law says that there is an integral of H around the contour C. Symmetry requires that only the azimuthal component of H be non-zero and that this component only depend on the radial position R. The line integral is simply the product of H phi and the circumference 2 pi r. The surface integral is the total current I. H phi is inversely proportional to R. H phi is proportional to I. In our experiment, the wire is horizontal. Here is the wire. Ampere's law predicts the magnetic field intensity as it depends on R. H sub phi is inversely proportional to R. This Hall effect probe measures the magnetic field intensity. The top trace on the oscilloscope is a measure of the probe output. The lower trace measures the wire current. The wire current is measured by measuring the voltage drop across a series 1 ohm resistor. We measure 6 volts peak, so the current is 6 amperes peak. This probe measures magnetic field intensities perpendicular to its flat surface. When aligned in this direction, it measures the Z component of magnetic field, about 0. When aligned in this position, it measures the radial component of magnetic field, again about 0. When aligned in this position, it measures the phi component of magnetic field, which seems to be the only non-zero component of magnetic field. For a current of 6 amps, Ampere's integral law predicts this 1 over R radial dependence for H sub phi. Our measurements are limited to distances r small compared to the distances to the end of the wires or to the return wires below. Because the Hall effect probe fundamentally exploits the Lorentz force law, it measures the flux density mu naught H. A common unit for flux density is the Gauss. We have to take this into account in evaluating Ampere's law. For conversion of units, 10,000 Gauss equal 1 Tesla, where the Tesla is the SI unit. With the probe at 1 centimeter, the measured flux density is 1.2 Gauss peak. I is 6 amps. R is 1 centimeter. So we calculate mu naught H phi to be 1.2 Gauss. Here is the data point on our plot. Here are some other measured values. We have demonstrated the relationship between current through a surface S and magnetic field intensity integrated around the contour C given by Ampere's integral law. Faraday's integral law shows how a voltmeter reading induced by magnetic induction at the terminals of a coil provides a measurement of the magnetic flux density. Faraday's integral law states that the circulation of electric field E around a closed contour C is determined by the time rate of magnetic flux linking the surface enclosed by the contour. The circulation of electric field E around the closed contour C is determined by the time rate of magnetic flux linking the surface enclosed by the contour. In this experiment, the contour C is traced out by the wire in this coil, so that the surface S is the area having the entire length of the coil as its edge. In this coil, the surface area S is 8 centimeters by 21 centimeters multiplied by 20 turns. We will use this coil with Faraday's law to find the magnetic flux associated with current in this wire. Here is the wire carrying a current I, producing this magnetic field, H sub phi. Here is our coil. In accordance with Ampere's integral law, the magnetic field intensity circulates around the current carried by the wire. The magnetic flux passing through the coil contributes to the surface integral on the right in Faraday's law. The current and hence the field are varying at 60 Hertz, so this integral has a time rate of change. Applied to the coil, the line integral on the left becomes the negative of the terminal electromotive force or voltage. Here is the induced voltage in the coil. The total flux linked by the coil is lambda sub F. The upper trace of this oscilloscope records the electromotive force or voltage at the coil terminals. The lower trace is the current in the wire, measured by the voltage drop across a 1 ohm series resistor. With the coil rotated so that it links no magnetic flux, no voltage is seen. With the coil now placed so that the magnetic flux passes perpendicularly through the coil, the maximum signal is recorded. With the coil straddling the wire, the flux passing through the coil in the upper section is oppositely directed to the flux through the lower section. With it symmetrically positioned, the next net flux is 0, so the measured voltage is 0. The scope traces are triggered on the wire current, the lower trace, so we can see the change in phase as the coil is moved from below the wire to above the wire. The lower trace current is 90 degrees out of phase with the upper trace induced voltage. This is because the coil voltage is the time rate of change of the magnetic flux, and hence of the time rate of change of the current. The coil voltage is 90 degrees out of phase with the current. The coil height is h, the length is L, and the number of turns is N. In terms of these parameters, this is the flux linkage. The flux linkage for a single turn is the surface integral. The total flux linked is obtained by multiplying by N. R is the distance from the wire to the top of the coil. In the experiment, this distance is R. Faraday's law gives this as the coil voltage. To put data on a plot of normalized voltage as a function of normalized spacing, we compute V sub 0. The coil has 20 turns, a length of 21 centimeters, and the frequency is 60 Hertz. The peak wire current is 6 amperes. Then V sub 0 is 1.9 millivolts peak. With the spacing R equal to 6.5 centimeters, the peak coil voltage measured at the terminals is about 2 millivolts peak. Here is the normalized voltage predicted by Faraday's integral law as a function of normalized spacing. Our data point goes here. These are normalized voltages measured at other spacings. The discrepancy is due to the large sensing coil size as compared to the length of the current carrying wire and the proximity of the nearby return current wire. Faraday's integral law predicts the voltage induced at the terminals of a coil that links a time-varying magnetic flux. In practice, this circular conductor could be a high-voltage power line, and this conducting ground plane could be the earth underneath. The potential between the conductor and the ground plane is that of two line charges, one just below the center of the conductor, and the other, its image, symmetrically located below the ground plane. Here are these line charges, one just below the center of the conductor, and its image here below the ground plane. With the line charges at these positions, the equipotential surfaces are cylinders, including, as a limiting case, the x equals 0 symmetry plane. The value of A is just that which makes the cylinder of radius r an equipotential surface. We apply a voltage from this 100 Hertz source to the circular conductor. The actual charges are induced on its surface in just such a way that every point has the same potential as the source. Similarly, charges are induced on the surface of the ground plane in just such a way as to make it have zero potential. We can measure the charge induced on the ground plane with this probe. The probe has a center section electrically insulating from the surrounding shield, which contacts the ground plane. The surface charge density distribution on the ground plane is proportional to the normal component of the electric field. It is therefore proportional to the voltage of the cylinder. Conservation of charge requires that the probe current be the time rate of change of the charge on the probe surface. It follows that the voltage induced across the internal resistance of the scope is proportional to the rate of change of the applied voltage. The upper trace is the applied voltage. The lower one is that of the probe. Because the probe voltage is the time derivative of the applied voltage, the signals are 90 degrees out of phase. Our line charge potentials predict the probe voltage. Y is the location of the probe on the ground plane. Y measures the distance to the probe from the center line. This is the predicted distribution of normalized probe signal with normalized probe position. The signal is largest directly under the conductor, trailing off to zero as the probe is pulled away. As the probe is moved out from under the conductor, the lower scope trace shows the charge induced on its surface decreases. Let's make a quantitative comparison of what we predict and what we measure. For our experiment, the scope resistance is 1 megohm. The probe area is pi times 3 centimeters squared. The capacitance per unit length between the cylinder and the ground plane is calculated to be 23.8 picofarads per meter. The applied voltage is 10 volts peak, and the frequency is 100 hertz. A, the distance from the image charge to the ground plane, is calculated as 10.8 centimeters. Then V0, the voltage with the probe directly centered under the cylinder, is calculated as 1.25 millivolts peak. This compares to a measured value of about 1.15 millivolts peak. Our theory gives an absolute prediction to within 10%. This is consistent with sources of error, such as the finite probe area. To test the prediction of the shape of this distribution, we have taken these data points. So that the shapes can be compared, the probe voltages have been normalized to the value V0 measured at y equals 0. In the analysis, it is assumed that the plane is grounded. Presumably, even the section of surface occupied by the probe is constrained to zero potential. In computing the current to the probe using this assumption, and then finding the probe voltage, we are making an approximation that is valid only if the voltage is small. One way to ensure this is to make the resistance of the scope small. The scope resistance is 1 megohm. It may come as a surprise that such a resistance is treated here as a short circuit. However, at 100 Hertz, the voltage is small enough. We can see our approximation get into trouble by raising the frequency. Our formula says that the voltage should be proportional to the frequency. As the frequency is raised from 100 Hertz to 200 Hertz, the voltage does indeed essentially double, as the equation suggests. Remember, the lower trace is the probe voltage. But as the frequency is raised from 500 to 1000 Hertz, the probe signal saturates. As the frequency is raised to this range, the voltage of the probe becomes large enough that it does begin to influence the field distribution. Some of the field lines that originally terminated on the electrode are diverted to the grounded part of the plane. Also, charges of opposite polarity are induced on the other side of the probe, between the probe and the ground plane underneath. The result is an output signal that no longer increases with frequency. A frequency response of the probe voltage that does not increase linearly with frequency is therefore telltale evidence that the resistance is too large or the frequency too high. Electric fields at low frequency do not penetrate the body. Provided a person is grounded, the hand effectively shields the probe. Our experiment illustrates how the potential of two line charges can be used to predict the surface charge induced on a conducting surface.
The capacitance attenuator demonstrates the nature of solutions to Laplace's equation. This is the two-dimensional form of Laplace's equation in Cartesian coordinates, x and y. Product solutions to this equation illustrate the nature of a potential that is periodic in one direction, the x direction. The hyperbolic sine function, which is a combination of exponentials, represents the essentially exponential decay in a direction perpendicular to the direction of periodicity, y. The potential can be viewed as the vertical dimension on this floor. This is the potential. The x direction, the direction of periodicity, is that direction, and here's our sine function. This is the y direction, and here's our hyperbolic sine function. More of the x dependence and the y dependence. Lines of equipotential on our model are represented by these wires. Lines of constant altitude are the lines of equipotential. This particular one is rectangular. Here's another way to represent our potential function. This is the x direction, this is the y direction. With these clamps, we're holding the membrane down on these edges. On this edge, we're going to raise the potential. These boundaries are clamped to 0 potential, and now we've raised this potential to a potential V. Under uniform tension, the membrane altitude satisfies Laplace's equation. Far from the elevated edge, the membrane then has the same shape as with the model. Rather than using wires to show the lines of equal altitude, the equipotentials, we now use backlighting. Here's what it looks like from the top. The elevated potential is uniform. Not a sine function. However, the square distribution can be represented by a Fourier series. This amounts to a superposition of solutions like the one we've seen, except they have more wiggles in the x direction and therefore decay more rapidly in the y direction. What we see is the potential if 3 of the walls enclosing a rectangular region are grounded, and the 4th has a uniform distribution in potential. The electric field lines are perpendicular to the equipotentials and follow paths of steepest descent. If they begin on positive charges here, they terminate on negative charges on the boundaries. A boundary that has 0 potential nevertheless supports surface charges. The surface charge is proportional to the slope of the adjacent potential. This is a cross-section of the electrical system that has been pictured. These boundaries are grounded, while this one is at the potential V. If V were positive, this charge on the lower surface would be negative. In the actual experiment, a conducting box is grounded on 2 side surfaces and virtually grounded on the bottom surface through a small resistor R. In the experiment, the resistance R is the 1 megohm resistance of this scope, which is used to measure the voltage of the lower electrode. Here are the grounded side walls. Their spacing is A. The top electrode, here a distance B above, is driven by this AC source. Here's the top electrode. Its potential is determined by the oscillator. That's the top trace of the scope pattern. Here's the bottom electrode. Its potential is measured by the bottom trace on the scope. We'll use our solutions to Laplace's equation to find the net charge on the lower electrode. Before we make any measurements, we should put our second sidewall on the apparatus. Conservation of charge requires that the current through the 1 megohm resistance of the scope be the rate of change of this charge with respect to time. Q is proportional to the driving voltage. Our input voltage varies sinusoidally in time, so the measured output voltage is 90 degrees out of phase with the input voltage. Our modal solution predicts the normalized peak amplitude of this output voltage, V sub O. U is proportional to the input voltage, V. The experiment is designed to demonstrate the dependence of the output voltage on the spacing B, the spacing between the input and output electrodes. The decay of the potential in the direction perpendicular to the electrode is the reason for the hyperbolic sign in the denominator. According to our theory, the natural log of the normalized output voltage has this dependence on the distance between input and output electrodes. On the log plot, with increasing B over A, the function quickly becomes a straight line with a slope minus pi. As the lower electrode is withdrawn, its potential decreases exponentially. The output voltage decays with electrode spacing because charges induced on the input electrode have their images either on the side walls of the box or on the output electrode. If B over A is small, almost all of the images are on the output electrode. But as we withdraw it, more and more of the images are on the side walls and fewer on the output electrode. How well does the theory predict this attenuation curve? Here are the numbers. To put data on our normalized plot, we first evaluate U. We have a width W of 17 centimeters. The frequency, 100 hertz. The scope resistance is 1 megohm. With an input of 10 volts peak, U equal 48 millivolts peak. For A equal 4.4 centimeters, and a spacing between input and output electrodes B equal 1 centimeter, we measure 28 millivolts peak. This data point falls about here. Here are some other data points that we've taken. According to our model, the output voltage should be proportional to the frequency. This is true if the frequency is taken from 100 hertz to 200 hertz. Remember, the upper trace is the upper driving electrode, and on a different scale, the lower one is the lower electrode voltage. However, if the frequency is taken from 1,000 hertz to 2,000 hertz, the output ceases to be linear in the frequency. With the frequency this high, the current through the output resistor is too large to make the potential of the output electrode negligible. We have demonstrated how solutions to Laplace's equation that are periodic in one direction decay in the perpendicular direction. An artificial dielectric made from an array of conducting spheres demonstrates how polarization of media gives rise to the properties of a linear dielectric. When the region between electrodes is filled with a dielectric material, the capacitance is increased. This increase is due to polarization of molecules of the material. We form an appreciation for how this happens by replacing the molecules with macroscopic spheres suspended in air. This artificial dielectric is composed of what we can think of as molecules that are actually essentially perfectly conducting spheres. Each has radius r, and they're in a cubic array with spacing s. Application of voltage to the electrodes results in the spheres acquiring positive and negative surface charges on their poles. In addition to the uniform field, due to the applied voltage, the field outside the spheres also includes the dipole fields from the array of spheres. The spheres, like the molecules of a material, are polarized by an applied field. The artificial dielectric is composed of an array of ping-pong balls with conducting coatings. We're going to measure the effective permittivity by measuring the change in capacitance as the array is placed between the plates of this plain parallel plate capacitor. The cage is grounded for shielding and to keep us from touching the bottom electrode. It's driven to 400 volts RMS at 250 hertz by this transformer, which is itself driven by an oscillator and amplifier. Here's the top electrode. To avoid fringing effects, only the charge induced on this central section will be measured when we measure the capacitance. Here's how the dielectric is inserted between the plates. This is a picture of the experiment. Here's the transformer driving the lower electrode. Here's the top plate connected to one side of a differential amplifier. Because the spacing between spheres is more than 2 diameters, the increase in capacitance caused by the spheres is small. To measure the small change in capacitance that results from inserting the array, the parallel plate capacitor is in one leg of a bridge. These capacitors are in the other legs of the bridge. It helps to draw the circuit like this. Here are the ping-pong balls. These capacitors are those of the balanced amplifiers on the scope. So the oscilloscope displays the output voltage, V sub 0. With the array removed, this capacitor, C sub 2, is adjusted to null the output voltage, V sub 0. The output voltage resulting from the insertion of the array is a measure of the change in capacitance. To simplify the interpretation of this voltage, the resistances R sub S are made small compared to the impedance of the parallel plate capacitor. They're 100 kiloohms. As a result, almost all of the applied voltage V from the transformer appears across the lower legs of the bridge. With the introduction of the array, there's a change in current through the parallel plate capacitor. This results in a change in current in the resistance in the right leg, and hence a change of voltage across the resistance. Because the current through the left leg has remained essentially the same, this change in voltage is the measured output voltage. With many widely spaced and therefore non-interacting spheres, the effective susceptibility and the changing capacitance caused by inserting the array between the plates are given by these expressions. Remember, R is the radius of a ping pong ball, and S is the spacing between balls. A is the active area of an electrode, and D is the spacing. So this is the capacitance without the array. The radius of the ping pong balls is 1.87 centimeters. The spacing S is 8 centimeters. The electric susceptibility is then 0.16. This means that the relative permittivity is 1.16. To compute the resulting change in capacitance, we multiply the susceptibility we've computed by the electrode area, 0.4 meter squared, the permittivity of free space, and divide by the electrode spacing, D, 15 centimeters. So the predicted change in capacitance is 1.5 picofarads. What change in voltage should we measure when the array is inserted? Here's what we predict. For our experiment, R sub S is 100 kiloohms. The frequency F is 250 hertz. Delta C is 1.5 picofarads. And V is 400 volts RMS, or 566 volts peak. For this applied voltage, this change in capacitance should result in a change in voltage of 133 millivolts peak. Before balancing the bridge, we remove the array of ping pong balls. We've already set the driving voltage to about 400 volts RMS. Here are the resistors in the two upper legs of the bridge. They shunt the scope differential amplifier. So the scope signal is the voltage V sub 0. The balancing capacitance, C2, is here. This is the capacitor, C1, which is there for fine-tuning. We can balance the signal with this capacitor. So we tune C2 to null the bridge voltage, and C1 to fine-tune the null. We're ready to insert the artificial dielectric. As the array is inserted, the bridge becomes unbalanced, indicating that the capacitance is changed. We measure a voltage of 135 millivolts peak. Remember, what we predicted was a change of 133 millivolts peak. The agreement is perhaps better than we should expect. Has the capacitance actually been increased by the insertion of the spheres? Let's try the experiment again. We can see that it has by looking at the balancing capacitor. Here, the array is out, and we balance the capacitor. Now we insert the array. Note the position of the tuning capacitor plates. If the capacitance has been increased to balance the bridge, the knob must be turned so that they have greater area of overlap. The balancing capacitance is increased, so the artificial dielectric does increase the capacitance of the plain parallel capacitor. Our model for how the polarization of the spheres increases the capacitance appears to be a good one. It is because the individual spheres have a polarizability that we can calculate, and because they're well removed from each other, that we can predict the equivalent permittivity of the artificial dielectric. Insertion of the artificial dielectric increases the capacitance.
Surface currents induced in a ground plane by an overhead conductor illustrate the method of images. Also illustrated is the superposition of fields due to line currents to satisfy boundary conditions. Here is a metal cylinder mounted over a metal ground plane. The cylinder is shorted to the ground plane at one end and driven by a current source at the other. This is familiar as an EQS situation where the same cylinder is insulated from the same ground plane and driven by a voltage source. Now the situation is magneto-quasi-static, MQS. Here's the metal cylinder mounted over the metal ground plane. The cylinder is driven by a current source at one end and is shorted to the ground plane at the other end. The ground plane consists of an aluminum sheet having a thickness of about 1 millimeter. It's resting on a plywood base. Our magnetic field is the same as that due to a line current here, just below the center of the conductor, and its image here, below the ground plane. With the line currents at these positions, the cylinder has no normal component of magnetic field. The value of A is just that for which the cylinder of radius r has no perpendicular component of magnetic field. These are the field lines produced by the line currents. The field is tangential to the surface of the cylinder and to the midplane. Thus, these surfaces can be replaced by the metal surfaces of the cylinder and ground plane. The fields are terminated by surface currents in the cylinder and in the ground plane. The image line current contributes to the magnetic field above the ground plane in exactly the same way as the actual surface current, which is non-uniformly distributed along the ground plane surface. When we drive a current from a 3 kilohertz source through the circular conductor, the actual currents are in the metal conductor walls, distributed in just such a way that there is no magnetic flux normal to every point on a given conductor surface. Similarly, these currents are returned in the ground plane in just such a way that there is essentially no magnetic flux density normal to the ground plane either. We can measure the magnetic field using this induction coil. The induced voltage is related through Faraday's law to the time rate of change of the linked magnetic flux. Thus, the amplitude of the probe voltage is proportional to the flux density, the average probe area, the number of turns, and the angular frequency. Our coil has an effective area of pi 0.85 centimeters squared, 200 turns, and an angular frequency of 2 pi times our frequency, which is 3 kilohertz. In this demonstration, a typical measured flux density of 0.11 Gauss peak gives an induced voltage of 9.5 millivolts peak. With the coil oriented this way, the vertical field component is recorded. When oriented this way, the horizontal field component is measured. Here at the center line, the tangential field is horizontal, just because of symmetry. Let's see if the flux density normal to the conducting sheet does tend to be 0 off the center line. Here to the side, the normal flux density appears to remain small compared to that tangential. So the current is returned in the sheet with just that distribution required to make the normal flux density small. Our equivalent line currents can be used to predict the flux density tangential to the sheet as measured by the sensing coil. L is the conductor height, and R is its radius. Then the height of the equivalent line current, A, is defined like this. Y is the location of the probe on the ground plane. Here is the Y dependence of the tangential flux density at the ground plane. This is the predicted distribution of normalized magnetic field with normalized probe position. H0 is the magnetic field at y equals 0. The tangential magnetic field is largest directly under the conductor, trailing off to 0 as the probe is pulled away. As the sensing coil is moved out from under the conductor, the tangential flux density decreases. Because there is little normal flux density just above the sheet, there is little of either of the components of magnetic field below the sheet. So what we see is the distribution of surface current density returning in the sheet. At high frequency, the current distributes itself in the sheet in just such a way as to make the normal flux density near 0. Our theory predicts the flux density at the center line, where y equals 0. Our current is 3 amps. The conductor height is 11 centimeters, and its radius is 2.1 centimeter. So A is 10.8 centimeters. The predicted flux density is then 0.11 Gauss. Directly under the conductor, carrying a 3 amp peak current, as shown in the upper scope trace, we measure 9.5 millivolts peak on the lower trace. This corresponds to 0.11 Gauss peak. This is in better agreement with the theory than we have a right to expect, given such factors as the size of the sensing coil. Here are some points that we have taken with this probe at different positions on the ground plane. Remember, this is the distribution of surface current density in the ground plane. Our experiments have shown that the perpendicular field at the surface of the ground plane is much smaller than the tangential field. This is true because the frequency of 3 kilohertz is high enough that the ground plane behaves as a perfect conductor. Let's see what happens if we lower the frequency. If we reduce the frequency by 10 to 300 hertz, the induced voltage decreases by 10. That's just because of Faraday's law. So let's compensate by turning up the scope gain by 10. At this lower frequency, we see that the ratio of normal component to tangential component is larger than at 3 kilohertz. At 300 hertz, here's the tangential component, and here's the normal component. At 3 kilohertz, here's the normal component, and here's the tangential component. At 3 kilohertz, the ground plane is thick enough to act as a perfect conductor, giving the tangential field predicted using the fields of a line current and its image. The fields of a circular cylindrical solenoid can be found using the Biot-Savart law. If these plane parallel plates were of infinite extent, an applied voltage would give an electric field that is uniform. What this plane parallel capacitor is to electric fields, an infinitely long solenoid is to magnetic fields. That is, if this solenoid were infinitely long, a current in the winding would produce a magnetic field intensity that is essentially uniform inside and equal to the surface current density. Outside, the field would be essentially zero. This solenoid is large enough that we can poke around in it with a magnetometer probe and see how the magnetic field is actually distributed when the length is finite. The solenoidal coil consists of n turns, essentially uniformly wound over the length d, each turn carrying the same current I. The radius is a. The current I is essentially phi directed. This axial Hall probe shows us the magnitude and direction of the field. The probe measures the field along its axis. The lower scope trace records the probe output. The upper scope trace shows the coil current. When the probe is oriented this way, the axial component of magnetic field is measured. When the probe is oriented this way, the radial component of magnetic field is measured. Let's measure the axial magnetic field component along the axis of the cylinder. On the axis, the radial component is of course zero because of symmetry. Well inside the solenoid, the field intensity in the z direction tends to be uniform everywhere. The infinitely long solenoid can be regarded as the analog for MQS systems of the EQS plane parallel plate capacitor. Well away from the ends, the axial field, just inside the coil, should be equal to the surface current density. The surface current density is the number of turns times the current per turn divided by the length d. The probe measures the flux density mu naught h. To convert from SI units Tesla to Gauss, we multiply by 10,000. There are 141 turns. Our current is 1 amp RMS, and the coil length is 70.5 centimeters. The predicted flux density, just inside the coil, is 2.5 Gauss RMS. This is on the order of the steady flux density produced by currents inside the Earth, so that we can distinguish our fields we are using a 60 Hertz current. Let's measure the magnetic field well inside the solenoid. We measure about 2.3 Gauss just inside the winding, as compared to the prediction of 2.5 Gauss. Let's see what the tangential flux density is just outside at the same axial location. Just outside, the flux density falls by more than a factor of 10 to 0.15 Gauss. Just as the capacitor can be constructed to create a uniform electric field between the plates with zero field outside the region bounded by the plates, so too the long solenoid gives rise to a uniform magnetic field throughout the interior region. Our solenoid length is finite, so the field inside is only approximately uniform. And the exterior field is only approximately zero. The magnetic field along the z-axis can be found by simple integration of the Biot-Savart law. The essentially phi-directed current along the entire winding generates a z-directed magnetic field along the axis of the cylinder. This is the on-axis distribution of the axial field intensity for our solenoid, which has a length-to-diameter ratio of 2.58. We can compare the prediction of this formula to our experiment here at the end of the solenoid. Biot-Savart predicts a flux density of about half of the 2.5 Gauss in the interior. Here's the on-axis magnetic field well inside the solenoid, about 2.3 Gauss. Here at the end of the coil, we measure about 1.2 Gauss, about half of the interior field. This is where our data points fall on the theoretical curve. Here's the interior point. Here's the point at the end of the coil. The accuracy with which theory and experiment agree is likely to be limited only by such matters as the uniformity of the winding, the care taken in mounting the probe, and the calibration of the Gauss meter. Another way to demonstrate the discontinuity in magnetic field between inside and outside the solenoid is to use this transverse probe. This probe measures magnetic fields transverse to its flat surface. Here, for example, is the on-axis field. Turning the probe by 90 degrees gives a zero signal, which shows the field is purely axial. We now place this probe just outside the solenoid in the orientation to measure the small tangential field component. As the probe passes through the current-carrying winding, the magnetic field abruptly rises to the interior field value. The field of a square pair of coils can be found by using the Biot-Savart law. The pair is often called a Helmholtz coil when the windings are connected so that the currents produce axial fields that reinforce. It can then be used to make a relatively uniform field in the mid-region, which is accessible for experiments. The Biot-Savart superposition integral can be used to find the field at the observer coordinate r. Its evaluation amounts to a summation of the field contributions from each of the differential size current elements at the source coordinate r prime. Our square coils are composed of connected straight-line current segments, or current sticks. The Biot-Savart law is used to find the field at an arbitrary observer position r, associated with each current stick. Because the individual current sticks do not represent the solenoidal current density at its ends, the magnetic field derived is of physical significance only if used in conjunction with other current sticks that together form a continuous current distribution. Each of our square coils is composed of 4 connected current sticks. The magnetic field at point P is found by a summation of fields from each stick. Each coil has n turns carrying a current I with sides of length 2d. The current I in each coil is in the same direction, so that the magnetic field induced by each coil reinforce along the minus z axis. For the direction of current shown, the right-hand rule shows that the axial magnetic field is in the minus z direction. Because of the axial symmetry the fields along the z-axis induced by each of the sides of the coil at z equal d are the same. Evaluation of the Biot-Savart law for both square coils therefore gives this variation of the axial magnetic field as a function of axial position z. The first term is due to the coil at z equal d. The coil at z equal minus d makes a similar contribution, except that the term 1 minus z over d is replaced by 1 plus z over d. In the experiment, the axial field produced by currents in the two square coils is probed by means of a Hall magnetometer. The output is connected to the vertical trace of a high persistent scope. The probe is mounted on a motor-driven carriage that is attached to a potentiometer in such a way that there is an output voltage proportional to the horizontal position of the probe. This is used to control the horizontal scope deflection. The result is a trace that follows the predicted z-dependence of the magnetic field along the symmetry axis. Here are our square coils, each with 50 turns, and sides of length 45 centimeters. The axial magnetometer probe is mounted on this carriage to record the z component of magnetic field. Before we apply current to the coils, we have compensated for the small part of the Earth's magnetic field that is in the horizontal direction by zeroing the magnetometer. The Earth's magnetic field is essentially vertical with a strength of about 1/2 Gauss and could contribute a slight error to the measurement if not accounted for. A current of 2.5 amperes is applied to the coils. We have placed the theoretical variation of the magnetic field versus position z as a solid line directly on the oscilloscope screen. Let's see if the scope trace follows this theoretical curve. We have adjusted the scope vertical gain so that the display matches the theoretical waveform at one position. We'll see if the scope trace follows the shape of this theoretical curve. We'll check the field magnitude later. The probe is initially here. We now turn on the probe carriage. The scope horizontal gain has been adjusted so that the horizontal deflection of the scope matches the z position of the probe. The magnetic field is largest directly under a coil. Now the left one at z equal minus d. And is fairly uniform in the central region between coils, with a minimum at the center, z equals 0. The field increases again to a maximum under the right coil at z equal d. And decreases in the region outside the coils. Let's compare the theoretical and measured field magnitude at z equals 0, midway between the coils. We bring the carriage back to the center, z equals 0. Full-scale deflection is 10 Gauss. We measure a magnetic field of about 2.4 Gauss. Let's compare to the predicted value. With 50 turns, a current of 2.5 amperes, and a half-side dimension of 22.5 centimeters, the predicted magnetic flux density is 2.6 Gauss. To convert from Teslas to Gauss, we have multiplied by 10,000. We measured 2.4 Gauss. In our Helmholtz coil experiment, the current in each coil was in the same direction, so that the axial magnetic fields from each coil reinforced. With the current reversed in the left coil, the axial magnetic fields of each coil are oppositely directed and cancel in the center. This results in a sign reversal for the field contribution from the left coil. Now the magnetic field is an odd function around z equals 0. It is 0 in the center as expected. This reversing switch reverses the direction of current in the left coil. Let's see how the measured field compares with the prediction. We have aligned the zero field lines and adjusted the vertical gain to match the waveform at one point. We now turn on the probe carriage. The field is a negative maximum under the left coil. Is 0 at the center. And reaches a positive maximum under the right coil. Using a pair of square coils, we have demonstrated the power of the Biot-Savart law in predicting the magnetic field distribution. Given the distribution of current, and given that there are no effects of magnetizable materials, this law gives precise predictions. For a many-turn coil, the surface used to define the flux linkage is often geometrically complex. Faraday's law equates the circulation of electric field around a closed contour C to the negative of the time rate of magnetic flux passing through any surface S bounded by the contour. Any shaped surface can be used, just as long as it is bounded by the contour C. A many-turn coil having terminals at A and B links flux through the surface enclosed by a contour composed of C1 adjacent to the perfectly conducting wire and C2 completing the circuit between the terminals. The direction of positive flux is that of area element dA, defined with respect to differential length element ds by the right-hand rule. If the terminal voltage is to be a uniquely defined quantity, independent of the layout of the connecting wires, the terminals at A and B of the coil must be in a region where the magnetic induction is negligible compared to that within the coil interior. To visualize this complex surface enclosed by the contour C1 plus C2, we use yarn strung on a frame representing the contour. For this three-turn coil, the surface is filled in by stringing yarn between a vertical rod joining the terminals in the external region to points on the wire. The surface is filled in by connecting points on the rod to points of increasing distance along the wire. In evaluating Faraday's law, the contour goes from the terminal at A to that of B along the coil wire and closes through a path outside the coil. However, the electric field E is 0 along the perfectly conducting wire. Hence, the entire contribution to the line integral comes from the path between the terminals from B to A. Thus, the circulation of electric field E around the closed contour is just the negative of the terminal voltage of terminal A with respect to B. Faraday's law then requires that this negative of the terminal voltage just equal the negative of the time rate of magnetic flux lambda through the surface. The surface S spans the entire closed contour. The surface S has as its edge the perfectly conducting coil along C1 and the contour C2 used to close the circuit in the region of the terminals. The surface S includes the sum of areas enclosed by each individual turn. If the magnetic induction is negligible in the region of C2, the electric field is irrotational in the vicinity of the terminals. Then the specific contour C2 is arbitrary, and the electromotive force between the terminals becomes the voltage used in circuit theory. A circuit application of Faraday's law is an inductor. When the flux linked by a perfectly conducting coil is due entirely to the current I in the coil itself, the magnetic flux lambda is proportional to I. The ratio of flux to current is the self-inductance L. The dependence of the inductance L on the number of turns in surface S is a way of demonstrating how the terminal voltage depends on the time rate of change of the total flux linked by all coil turns. The inductance is only a function of geometric variables like coil size, number of turns, and for linear magnetic materials, the magnetic permeability of the region inside and outside the coil. We have wound a few inductors of different lengths and number of turns on a wooden rod using copper wire covered with enamel insulation. The enamel insulation prevents electrical contact between turns, so the current path must follow the wire. The insulation prevents short-circuiting between turns. We will measure the coil inductances using this meter. Because the coil length D is much larger than the coil diameter, the magnetic field within the coil carrying a current I is approximately uniform over the coil cross-section. The tightly wound end-turned coil approximates a surface current with current per unit length of Ni over D. Because the magnetic field outside a long coil is negligible, the discontinuity in tangential H is just the interior magnetic field. This field must then equal the surface current. Because the field is uniform over the circular cylindrical cross-section, the magnetic flux phi sub lambda passing through one turn is simply the cross-sectional area multiplied by the flux density mu naught H. The total flux linkage of the entire coil is obtained by summing the contributions of all the turns. In this simple case, all turns link the same flux phi sub lambda, so the total flux lambda is n times the flux linked by each turn. Since the flux per turn is already proportional to n, the self-inductance is proportional to the square of the number of turns. We have twisted the terminal ends of this coil to reduce the stray inductance. It is wound on the non-magnetic rod, which has a radius of 5 millimeters. This coil has 50 turns and is 5.05 centimeters long. The coil inductance is predicted to be 4.9 microhenries. The inductance meter measures the coil inductance at 1 kilohertz. This frequency is high enough that the coil inductive reactance greatly exceeds the small coil of resistance, which we have neglected in our analysis. We measure 5.9 microhenries. This inductance has contributions from the coil and connecting wires. We short-circuit the terminals and measure 0.7 microhenries as the lead inductance. Subtracting this from the measured 5.9 microhenries gives the coil inductance as 5.2 microhenries, in reasonable agreement with the predicted 4.9 microhenries. We now measure the inductance of the coil with double the number of turns, but also double the length. Doubling the number of turns n, but also doubling the coil length d, should result in double the inductance. The inductance meter now reads 11.2 microhenries. Subtracting the 0.7 microhenry lead inductance gives corrected coil inductance of 10.5 microhenries, about double the inductance of the first coil of 5.2 microhenries, as it should be. We now measure the inductance of the coil, which is the same length as the second coil, but has 2 layers of windings and thus double the number of turns. We measure 44.4 microhenries, for which the corrected coil inductance is 43.7 microhenries. We have doubled the number of turns without changing the coil length. The coil area of the two-layer coil is hardly changed because the wire diameter is much smaller than the wood diameter used as a core form. The inductance should increase by 4. This coil inductance is about 4 times our previous corrected measurement of 10.5 microhenries with half the number of turns. The surface for a many-turn coil used in Faraday's law is geometrically complex, as the bounding contour to the surface follows the path of the wire. For a tightly wound coil, the magnetic flux linking this surface is the sum of fluxes linking each turn. Since the magnetic flux per turn is proportional to the number of turns, if each turn links the same flux, the total flux linked by the coil is n times the flux per turn. The coil self-inductance is then proportional to the square of the number of turns. Measurement of the BH characteristic of a magnetizable core provides the constitutive law that relates the magnetization density M, or equivalently the magnetic flux density B, to the macroscopic magnetic field intensity H within a material. The objective here is to observe the establishment of H by an imposed current in accordance with Ampere's law, and to deduce B from the voltage it induces in accordance with Faraday's law. A toroidal coil is tightly wound onto a donut-shaped magnetizable core. Each turn carries a current I. For the toroidal geometry, Ampere's integral law is enough to relate the current I to the H field in the magnetizable core material. Symmetry about the toroidal axis suggests that H is phi-directed. Ampere's integral law is written for a contour C circulating about the toroidal axis within the core. Because the major radius R of the torus is large compared to the minor radius, the field is essentially uniform over the cross-section of the torus. We approximate the average radius by the radius R. Thus, the line integral of H is essentially 2 pi r times H. To evaluate the right-hand side of Ampere's law, we see that the surface S, spanned by this contour C, is pierced by the current I as many times as there are turns N1. So the surface integral of J is N1I. Thus, Ampere's law reduces to the product of H phi and the contour circumference 2 pi r equaling N1I. Here is the excitation winding. The current is supplied by this variac. The voltage drop across this small resistance in series with the driving winding is used to record the driving current I. This voltage drives the horizontal amplifier of the oscilloscope. Because the H field is proportional to current, the horizontal scope deflection is therefore proportional to the magnetic field intensity H in the core material. The magnetic flux density is measured by means of a second sensing or secondary winding, also wound on the donut-shaped core. This coil is terminated in a high enough impedance that it carries a negligible current. Thus, the H field established by the current I of the excitation winding is unchanged. The flux linked by each turn of the sensing coil is essentially the flux density B multiplied by the cross-sectional area of the core. The flux linked by the N2 turn coil is then N2 times the flux linked by each turn. An RC integrating network on this sensing or secondary coil integrates the terminal voltage so that the flux linking the coil is recorded. The circuit acts as an integrator because the capacitor has a reactance at the frequency of operation, 60 Hertz, that is much smaller than the series resistance. With the capacitor essentially a short circuit, the current is approximately V2 over R2. From Faraday's law, the terminal voltage of the sensing coil is the time rate of change of the magnetic flux linking the coil. This current then charges the capacitor. By comparing these last two equations, we can see that the voltage across the capacitor is proportional to the magnetic flux linking the sensing coil. Thus, by connecting the terminals of the sensing coil through the integrator to the vertical trace of the oscilloscope, we make the vertical axis proportional to B. So, we should see a display of B versus H on the oscilloscope. Here is the experiment. The magnetizable material is in this donut-shaped toroid. The excitation or primary coil connected to these terminals is driven by the current at 60 Hertz from this variac. The voltage across this series 1 ohm resistance then gives a horizontal deflection of the oscilloscope proportional to I and thus H. The terminals of the sensing coil are connected through the integrating network with resistance 100 k ohms and capacitance 1 microfarad to the vertical deflection terminals of the oscilloscope. Thus, the vertical deflection is proportional to the integral of the terminal voltage, the flux lambda, and hence to B. We turn up the variac current. The scope shows the BH hysteresis loop typical of a magnetically soft material. For our primary coil of 83 turns, the major radius is about 3.2 centimeters. The current viewing resistor on the primary coil is 1 ohm. Thus, the scope scaling factor relating H to V1 equal IR1 is 413. With a horizontal scope scale of 0.5 volt per centimeter, each scope horizontal deflection of 1 centimeter is about 210 amps per meter. The minor diameter of the secondary coil is 1.2 centimeters. There are 537 turns. The integrating circuit has resistance 100 k ohms and capacitance 1 microfarad. The scaling factor relating integrating capacitive voltage V sub C to magnetic flux density B is 1.65. With a vertical scale of 0.5 volt per centimeter, each vertical deflection of 1 centimeter is 0.83 teslas. Thus, for this core, saturation is reached at B approximately 2 teslas for an H field of about 500 amps per meter. Polycrystalline ferromagnetic material at the domain level has randomly oriented magnetic moments that tend to cancel in the absence of an applied field. As a magnetic field is applied, the domain walls shift. Those domains with magnetic dipole moments aligned with the applied field grow at the expense of domains having oppositely directed magnetic dipole moments. The result is a net magnetization that tends to be in the direction of H. In ideal materials at high magnetic fields, saturation results when all of the domains combine into one. In real materials used for transformers, imperfections and boundaries result in the domain walls encountering a resistance to motion. A phase lag then develops between the magnetization and the magnetic field intensity H. The BH trajectory makes this evident. It shows that even when the applied field H is instantaneously zero, there remains a remnant flux density, B sub r, and the field must be reversed to minus H sub C, the coercive field intensity, to reduce the flux density to zero. Hysteresis can be both useful and harmful. Permanent magnetization at the remnants point is the basis for permanent magnets and for the storage of information on magnetic tapes and disks. However, periodic excitation of a hysteretic material, such as in a transformer or rotating machine, dissipates energy and generates heat. The area enclosed within the BH hysteresis loop is the energy per unit volume dissipated in one cycle. The dissipation arises from the resistance to propagation of the domain walls.
The non-uniqueness of voltage in an MQS system can seem paradoxical, yet it is essential to the behavior of a common transformer. When the electric field intensity is essentially irrotational, we can count on its having no circulation around a closed path. This means that its integral between 2 points is the same, regardless of path. If the magnetic flux density in Faraday's law is important, the line integral of the electric field intensity is path dependent. This experiment emphasizes this by showing how the voltages measured by these leads and the oscilloscope are path dependent. Here's the ground lead of the oscilloscope. Here's the top trace lead, and connected to the same point is this bottom trace lead. A magnetic flux is created in a toroidal magnetizable core by driving this winding with a sinusoidal current. Because it is a highly permeable ferrite, the core guides a magnetic flux density B that is much greater than that in the surrounding air. Looped in series around the core are 2 resistors of unequal values. The terminals of these resistors are connected together to form a pair of nodes. One of these nodes is grounded. The other is connected to high impedance oscilloscope inputs through the 2 leads that follow different paths. Here's the ground lead, and we'll use a dual trace oscilloscope to display the voltages. Here's the lead connected to the top trace, and then this lead is connected to the bottom trace. The voltages observed with the leads connected to the same node not only differ in magnitude, but are 180 degrees out of phase. The ratio of the voltage magnitudes is 3. This is the ratio of the resistances. The probes are connected to the same node, and yet the voltages differ by a factor of 3 and are 180 degrees out of phase. We check to see that we don't have the traces on different scales by reversing the trace connections. Reversal of the leads results in a reversal of the traces. Faraday's integral law accounts for this seeming failure of Kirchhoff's voltage law, for how it is that different voltages are measured by probes connected between the same nodes. This is a cross-section of the core. The pair of resistors are connected in series. The node that is connected to the ground terminal of each probe is here. One scope terminal is connected to the other node like this, while the other is connected like this. The scope resistances are very large compared to either R1 or to R2. So the current carried by the oscilloscope leads is negligible. This means that if there is a current I through one of the series resistors, it must be the same as that through the other. Because it encloses the time-varying magnetic flux carried by the core, there is a current circulating through the resistors. The induction of this current is predicted by Ohm's law and Faraday's integral law. Here, the key contour is the path of circulation through the resistors, and the surface cuts through the core. The voltage measured by trace 1 is determined by applying Faraday's integral law to this contour. Because it links a negligible magnetic flux, what is measured is just what is expected, the negative of the current times the resistance R sub 1. The voltage measured by trace 2 follows from this contour. It is the same current, but multiplied by plus R sub 2. The current out of the positive terminal of R sub 1 is that into the positive terminal of R sub 2. When voltage 1 is positive, voltage 2 must be negative. The ratio of the voltages is the negative ratio of the resistances. In our case, the ratio of the resistances is 30 ohms to 10 ohms, 3, just as we measured. If the probe leads follow the same paths, the signals should be the same. If we remove one of the leads and then connect the other one to its own ground, after having looped the lead through the core, what we see is this. Just as the series resistors form the secondary of a transformer, so now the lead itself is a one-turn secondary. The measured voltage is simply the time rate of change of the flux through the core. Visualization of standing waves that are electromagnetic requires that we see fields that are invisible and are varying at a frequency higher than we can actually perceive with our eyes. The visualization of waves that are mechanical is easier. Here we've got a spring under tension. The transverse deflections satisfy the wave equation. The object in this demonstration is to see standing waves in the sinusoidal steady state. Professor M.Zahn will provide a fixed termination at that end, and I'll try and provide the sinusoidal excitation. The first mode's pretty easy. Here's the second mode. A little harder to do. Try that again. At any location, the response is sinusoidal. We have a null in the middle because a wave incident on that termination comes back and interferes with the incident wave. Our objective here is to visualize not a mechanical, but rather an electromagnetic standing wave. Such a wave can be made to propagate between parallel metal plates. The electric field is directed from one plate to the other, terminating in plus and minus surface charges on the respective conductor surfaces. The magnetic field is tangential to the conductors. Terminating in positive and negative axial surface currents on the conductor surfaces. Both E and H are perpendicular to the direction of propagation. We therefore have a transverse electromagnetic wave. Such TEM waves can propagate on pairs of conductors of arbitrary shape, so we needn't be concerned with the width of the plates relative to the spacing. We're going to use a fluorescent lamp to give a rough indication of the amplitude of the electric field intensity. The electric field created by the wave will cause an ionization of the gas in the tube. The resulting light is therefore an indication of the distribution of the electric field intensity. This field is oscillating at more than 100 megahertz, so it's not possible for the eye to follow the oscillations. It's the envelope of the field distribution that we'll see. We can make standing waves by either short-circuiting or open-circuiting the line. Let's start with the plates shorted. Here are the actual plates and the short. They're driven at the left by a radio frequency generator. To see the lamp, we've turned the lights down. Next, the generator is turned on, and the lamp is put in place. I'm rubbing my feet on the carpet to generate static electricity to help ignite the lamp. Remember, where there's light, there's an oscillating electric field. The dark areas are therefore where the electric field tends to null. At the right end, we also appear to have a null. Remember, the right end is shorted. We can see the nulls even better if the lights are turned out completely. The electric field intensity is shorted out at the right termination. Here's the theoretical field distribution. The electric field amplitude is a maximum a quarter wavelength from the short, and at intervals of a half wavelength from that point to the left. What we see is the magnitude or envelope of the standing wave of electric field. We can think of the electric field between the plates as being analogous to the deflection of our spring. The deflection, like the electric field, is pinned to zero at the right end. The deflection, like both the electric and magnetic fields, is an oscillating function of time. It remains zero at the null points. The magnetic field amplitude is maximum near the short and at multiples of a half wavelength from the short. Not only are the peaks in magnetic and electric field displaced from each other spatially by a quarter wavelength, they're also 90 degrees out of phase in time. So when the electric field is maximum, the magnetic field is zero, and vice versa. The energy shifts from electric to magnetic form and back again in a half a cycle. We could measure the magnetic field with a one-turn induction coil. The coil voltage displayed on the scope indicates the magnetic field perpendicular to its axis. First, we put the coil at the null in electric field. The magnetic field is indeed tangential to the plates and perpendicular to the direction of propagation. The magnetic field should be a peak here, at the null in electric field. Now, moving toward the short, where the electric field is maximum, the magnetic field should null. And then, at the short, it should peak again. Note that the phase shifts by 180 degrees as we pass through the null. Standing waves also result if the plates are open circuit at the right end. Now there can be no current in the y direction in the plates at the end, and hence no tangential z-directed magnetic field between the plates there. With the magnetic field zero at the right termination, the electric field there is a maximum. It should peak at the termination and at half wavelength intervals to the left of the termination. Watch the peaks in intensity move by a quarter wavelength as the short is removed. Again, with the short on and with the short removed. It is the electric field intensity that is now the maximum at the right end. We see this better with the lights out. By measuring the distance between nulls in the electric field intensity, we determine the half wavelength. It appears to be about 70 centimeters. Electromagnetic waves propagate on the line at the velocity of light, c. So we can deduce the frequency of the source driving the plates at the left end. The frequency is equal to the velocity of light, 3 times 10 to the 8th meters per second, divided by the wavelength, about 1.4 meters. So the frequency must be about 210 megahertz. This is the frequency that we should deduce from the oscilloscope trace for the magnetic probe. The period is about 5.2 nanoseconds. The frequencies about 195 megahertz. The agreement with the 210 megahertz we found from the wavelength is consistent with the accuracy of our measurements. In visualizing electromagnetic standing waves, we've used the light illumination to indicate the electric field intensity and the probe to measure the magnetic field intensity. We've observed the distributions of E and H with open and short circuit terminations.